Cool. So as we studied last week, we looked at video compression in terms of, not the first video compression necessarily, but the, MPEG basically, MPEG-2. So the very popular, very ubiquitous MPEG. Now, you might be wondering, and as the question asks, what can we do that's extra to that? Because we kind of solved the problem in a lot of ways. But what can we do that's extra to that in order to score more compression? As we know, more modern compression systems have achieved more than MPEG has. And we are able to compress with higher ratios and better quality settings. I don't really like the term quality necessarily, but it is kind of perceptual quality. So what further work can we get, or what can we do in order to score more, essentially? Now, that naturally leads us, so this is where we could branch off into lots of different codecs here, but we're keeping it quite straightforward. So H.264 is kind of the natural one that goes past that point and is the kind of natural successor to the MPEG-2 codec. Now, funny thing about H.264, I remember when I was studying the same module, they were like, oh, it will be the future. And there was a very big debate around the idea, not really debate, but there was like an acknowledgement of the fact that you don't really get any extra compression for free. And so it wasn't that MPEG-2 and that system was just not very well conceived. It's a very good and very, it's an excellent compression system. The reason we didn't get any further than that for the years that it took to do that is because we had to wait for compute power to catch up. Any extra compression, as we'll see, all the extra things that we do take more churn, and we needed more space, more computational power. And again, at the time, we were at that point where, because I don't know, I'm getting old, I suppose, we were doing the course and we were talking about the fact that lots of people have got mobile phones these days, and the idea that H.264 might now become the new standard that mobile phones are able to decode. So it's not that you are really doing anything that's particularly better. They are just relying on higher computational power in order to generate this extra savings. So you can think of it that way. And this is why it's important, I think, to study this topic, because you aren't just throwing the best and latest tools at something. You have to think about your application. And as we'll see with H.265 and the more modern codecs these days, they are very computationally expensive. They require, in lots of cases, specific hardware. So it's not a case of just like, oh, we'll throw the biggest numbers at something. You have to think about what your application is. If you're designing something that's going to be run on a really cheapy, nasty little set-top box or something, or like a Fire Stick or those kind of devices, they might not have the computational power. I mean, these days they often do because they are designed that way, but they may not have the computational power that you need to decode some of the stuff that you might be encoding. So we have to be a bit careful. So H.264, which we'll focus on for the first few slides here, it's higher quality for the same kind of bit rate, and for the same quality, it's a lower bit rate, right? So the compression ratio is higher. And it's not free, as I've said. Your compression that you're achieving is achieved through computational power. And how do we do this? There's a bunch of these steps, right? So there's a bunch of stuff that we do in order to make it more better, more precise. So H.264, aka AVC, you might see these other terms used, or MPEG-4 Part 10, different names for the same technology. We have an advanced or more advanced motion compensation system. So we talked last week about the idea that we have difference frames, or we can encode differences between frames, and that's a smaller amount of data that we're sending than a whole fresh new frame. And we then discussed the idea that what we might do is take some pixels or groups of pixels and move them first. So we basically send some information about a direction of travel of those groups of pixels, and then we can basically move them and then do a difference frame, and that costs less for our difference frames. And the example that we gave in that particular lecture was that scene where we had that, again, panning. I can never remember the terms, panning, dollying, you know what I mean? The scene moved left to right, and it was that scene in Alien, right? So the whole scene is moving, and we had a big difference frame, but the actual pixels have all just moved right a little bit. So if we can put motion vectors on there, we can essentially move them first, and then do a difference frame after that, and it makes it cheaper. Well, the good thing, or the more advanced thing here with H.264 and this more modern codec is that it can use multiple sizes of blocks. So we've got, in MPEG-2, we used 16 by 16 block sizes, so they were only a set size. In H.264, we can go from 16 by 16 down to 4 by 4. So in areas where we get more motion or we want to be more accurate, we can move things, we can break those blocks down into smaller chunks, and those smaller chunks can be moved more accurately. And when we've got big, broad, kind of uniform, lack of detail, you know, the classic examples, the sky or the background or whatever, we can go for big sizes of blocks on those. And the bigger the sizes of the blocks, basically, the more we save. So there's a system where we can break those down and decisions are made on that, so we can change the size of the blocks. There is also a couple of other things that have been brought into that same system. So you've got the sub-pixel compensation. So in MPEG-2, it was half a pixel. We didn't really cover that last week, but you had half a pixel of accuracy. In H.264, and again, I think this costs more computational power, it goes down to a quarter pixel when you're moving the blocks around. So the idea is that when you make your differences or move your blocks to different places, they're more accurate, and therefore the differences are smaller. Differences being smaller means you save more data. And one of the big ones as well is that in our old MPEG system, we only had a single frame that we were referencing. So we had a single frame, and we said, right, what's the motion between that frame and this frame? In H.264, you can reference multiple frames and then predict the motion using multiple frames. So you can say, right, it's done this, 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 and this, so it's probably likely to do this. And the idea there, again, is that you end up with more predictable, more accurate predictions. Now, there was a point at which I was going to do a demo. Yeah, I think it's here. So here's an example. I should probably have loaded up the correct thing before I started this. So this program here is something called StreamEye, which is really cool. It's something I discovered actually just recently. And it really allows you to dig into this, these structures, all these different frames and how they're being generated. So for instance here we have, or I should probably load one just to be doubly sure. And then there's containers, so I'm not sure what they all are. I've forgotten this one. So this is an H.264 file. And you can see here, if we are to zoom in, we have different sizes of these blocks now. So if I turn the motion vectors off, and I can turn the partitions on, is that what I want? I believe so. So here you can see certain of these blocks are divided up into smaller chunks, basically. So if I mouse over them, I know this is very small for you guys, but if I mouse over them, you can see that this particular one has been divided up into the 4, and they are differences in size as you look around them. So each of those different macro blocks can be chunked up into smaller chunks, and you can see there an example where we've gone all the way down to those are 8 pixel ones, 8 by 8 pixel blocks. So in certain areas of the frame, you might be able to chop it up into smaller chunks, and that allows you to get more accurate prediction. And again, this tool is very useful because, as I said, you've got multiple frames now in terms of your prediction. You can actually see the frames that they're referencing using these arrows up here. So that B frame there is referencing all of those frames before it, I believe. Every time you click one, it tells you which ones it's referencing in order to make its decisions about its motion vectors. And like we did last week, if we click that button, we can actually see the motion vectors between each frame. So we can click frame by frame, and we can actually see the motion vector decisions that are being made for each frame. The other cool thing this software does is you can actually see the size of the frames as well, and you can see the savings we're winning here, right? So here, you can see the size of, what do you think that is? The big one. An iframe. So you can see the difference in the size of the iframes compared to all the different frame types there. You are saving an enormous amount of data, or data rate, or saving size, in order to, by doing this instead of sending individual iframes, right, every time. Sweet. It's just told me my evaluation has ended. So I'm hoping that I can still go through frames. Yes, I can. Okay, cool. So the third task for today is to download and install this and have a look at it. I don't think you're going to be able to do that on these computers, though. So I might ask you to take that away. Basically, this runs. We can get an evaluation copy, and that's what I'm running at the moment. For next year, I might see if we can get a couple of copies and install them in here, because it's such a useful tool for this particular thing. But you can kind of see all the different details it gives you. Really quite cool. So, and again, we can start to decode some of this. We've looked at subsampling, chroma subsampling, and you can see the scheme that we've got there, the chroma format. We can see things like the frame rate and the resolution, all that kind of stuff all comes from here. So we can start to decode some of this. It shouldn't really be too much of a hard thing to decode at this point. Cool. So better motion prediction. H.264 also has quite a clever thing, which is the DCT prediction as well. We've already looked at the JPEG DCT, the direct cosine transform, and the idea of how you can create an image from those spectral elements. And we played with some of those tools and looked at that. And then we discussed the idea that when you've got MPEG video, it just uses a JPEG as its iframe. Well, in H.264, it actually uses a predictive DCT as well. So what it means by that is, instead of you just having a separate DCT for every single one of your blocks, you might be inclined to say, right, well, in certain circumstances, though, those blocks might be quite similar. So why don't we predict the next block along, and then we can just send corrections rather similarly to how we do frame-to-frame prediction. So there's a bunch of these, and again, this is why this becomes really computationally expensive. You might be inclined to look downward to see if they're similar downward or horizontally or any other of these different factors. These are the ones that are available to you. So you've got to make a choice as to which one's going to give you the best compression ratio, and the way that you do that tends to be that you crunch through them and figure it out. So when you're compressing things in H.264 and H.265, it's harder, and this is where the computational, where the computational need comes from. So here we're basically saying, right, if we've got similar blocks, which happens quite often, why don't we just copy them and then we can correct them after that? And that makes, by only sending the corrections, then you're lowering the data burden in that manner. Another useful thing, I couldn't find a better picture than this stupid dude. It shows it the best way. I can show you something if the software allows me to in a moment, where we can remove the deblocking filter on a piece of video and you can see it before and after. But the effect actually is not massively profound unless the blocking is terrible. But in principle, there is a deblocking filter as well. So this essentially tries to smooth away the biggest issue you get with poorly compressed video. So if you are really trying to crush something down into very low bit rates, you'll start to see these kind of blocks. And H.264 will apply a filter just to sort of smooth those edges off. Let's be brave and have a look. So here's the software. Oh, apparently I'm not even allowed to, there we go. So if I am to open my tiny weeny little crushed up version of this same file, and turn off some of this stuff. I'll try and find a blocky bit. Which I'm probably not going to be able to find now that I'm actually looking for one. Oh no, hold on. It's the wrong file, that's why. No, it is that one. Sorry, I should have remembered each of what these files were called, shouldn't I? Well, this bit? Yeah, top of the tail, yeah, okay, yeah. And then if you click, there you go, there's it unfiltered, right? I bet it will snap away when I click decoded now. Oh no, there you go. I don't know if you can see that. Can you see that from there? I'll have to turn lights off and stuff. But essentially, if you click unfiltered, you can start to see the blocking. See chunks, like real blocks here. This is where the DCT is not, managing to, or the DCT and the codec together are managing not to give you the, they're giving you too much of a difference between each of those parts. and then it kind of just filters that away, which is useful. The other thing you can see here, I didn't show before, is you can actually see the parts of the frame. Like you remember last week I kind of contrived that thing with Photoshop where you could see the difference frames. This is actually showing you what the difference frame parts that it's working on, which is quite good. Which is cool. There you go. So we've got a deblocking filter. Now, that's good really, isn't it? Because if you think about, if you were to ask anybody off the street what poorly compressed video looks like, they will use that word, blocky. Pixelated, maybe they might say, but blocks. And I think I did that actually one of these weeks, didn't I? I said, what does poorly encoded video look like? So that's quite a useful thing. Another feature about H.264 that's quite useful, again, it's established that this is going to be, and especially when this was designed, it was established that this is going to be a really difficult thing to encode and decode. So as part of the process, they put together profiles so that they're scalable for different systems. And again, this is about quality to a certain extent, but really it's about the decoding power of the device that you're landing on. So you can use what they call the baseline profile, which should be quite easy to decode and encode, actually. Obviously, the decode process is simpler than the encoding process, but you should be able to, it's designed to give it a bit of backwards compatibility, essentially. Now, this is great, but you don't really know about this unless you're doing a talk like this. So this can be one of those things that's out in the wild that people don't really understand particularly well. So, standards I find these days are getting more and more complex, and that can be sort of difficult for normal people to understand. But essentially, it's a good idea because you can use the baseline profile, and then the normal ones they give are baseline, main, and high, but there are sort of variants within that as well, and there's also one for 10-bit color as well. So, the bit depth is higher on that one. So you've got options, essentially, when you go to encode this. So you've got scalability options, which is quite a nice one. Again, for things like from phones, you might not necessarily want to use all the processing power of things like phones because that eats through the battery and all that kind of stuff. So it depends what you're trying to do. And this is where it makes a lot of sense for you to be switched on to this, so you can actually understand how this stuff works and make useful decisions about this. Cool, so that's kind of H.264, and again, there's loads of other features in there, but we don't really, it doesn't make sense to cover it completely exhaustively. So those are the main features that allow it to be faster, or more compressed, sorry. Now, again, there was a further improvement, and you will have seen this probably out in the world. H.265 is gaining and being more and more adopted. And again, because we have now better processing, we've got better computational power. And in particular with H.265, specific hardware. So GPUs now, like graphics processing units that are in phones and computers and built into CPUs, like the ones that are in these computers, may well have some decoding and encoding support for this. They tend to be built into computers and stuff now so that we can use this. So, and when you have specific hardware built into your processing system, it makes it quite efficient. So this, you essentially optimize out a bit of the difficulty of having this system in play. So if you think it's difficult to do and therefore it doesn't get adopted, but if you actually adopt it into the hardware, it makes it easier and therefore you get all the gains, essentially. So how does this work then? How do we manage to get even more, or even more gains than we did? So this thing uses something called CTUs now instead of macro blocks. Which are essentially the same thing, but they are much more rangy. You get much more of a choice in terms of the size of them. So they can range all the way from 4x4, little tiny ones, all the way up to 64x64. And again, if I am to load one of these, if I did it right, where are we? There's an H.265 copy here. You can see the size of them all of a sudden. It looks like I'm really zoomed in, but the size of the CTUs, these big sort of blocks of pixels, you see they're 64 in size and then broken down into individual parts after that. So huge difference in the way that that kind of presents. And you can see the motion vectors there for each of those different parts. They look a bit wacky on that particular frame. but quite cool to be able to actually like dive in and see those. So because of the fact that those variable block sizes are quite, you can be very accurate where you need to be very accurate, and you can also be very broad brush where you want to do that. That means you are trading wherever is needed between compression and detail. And there's more improvement in terms of the motion compensation because of those blocks. And another clever thing that comes about is the idea of merging blocks that are kind of arbitrarily separated. One of the disadvantages of using a block system is that sometimes you might have blocks that are close to each other that might be different, and some of them that are close to each other that aren't different. And so by blocking up in a kind of grid square, you might be chunking things up that don't need to be separate. So there's a merging system within H.265 that allows you to merge together blocks that will travel together, essentially. So this is kind of a not particularly lovely example here, but you can see that we've got a piece of video here. There's this pendulum swinging or something. This is from some random research paper I found. And then it's made it into blocks, and then it's decided that these blocks need more detail because obviously it's moving right there. And then it's kind of used this merge mode to gather together these blocks here. So instead of having to describe each of these blocks individually, it's just describing all of that sort of mega block that's been merged together. And we can get some prediction there. As well as that, it's got better intra prediction. So that's the DCT prediction that I talked about earlier in H.264. There are more modes. So the 9 prediction modes we saw, let me go back, these ones. So these modes are available to us in H.264. In H.265, there's way more of them, basically. So we can decide to predict in way more directions, so 32 different modes of prediction. It's also got, H.264, one thing I didn't note is that it has adaptive streaming support. So as a connection quality changes, you can decide on different resolutions and bit rates. There's better support for that in H.265. It also supports more resolutions and bit depths and things like that for more modern displays. And nicely, it also supports much better the idea of multi-threading. As we know, through our work last year, we talked about how we have got cores in computers that go to certain speeds. Because of Moore's law and struggling with that, we've tended now to go with multi-cores instead of faster single-core processors. And now we're at the point really where you've got lots and lots of cores in particular computers. 4 to 8 to 16 is common. So we are much better able, if we can manage to support concurrent things happening in parallel, then they are faster. And that's what H.265 has better support for. As well as being able to be crunched on GPUs as well. Remember we talked about the idea that GPUs are like very simple cores, but millions of them, or thousands of them. Whereas CPU cores are very complex and clever, but there's only a few of them. So if we can separate this kind of work down into small jobs that can be done by GPU cores, then they can be parallelized and done much faster. So that's kind of where that comes along. And again, specific hardware is needed. For this kind of encoding, you're really looking at modern graphics processors, anything from about the NVIDIA 3000 series up, I believe. Thereabouts. Cool. So again, that's a bit of a whistle-stop tour. I don't know how important it is to go into miles of detail on this. Obviously, you get very computer sciencey, and it's an extremely important thing, but it's the kind of information you're never going to remember. The important thing is understanding what the differences are between them as we go through. So, what we're going to do for the rest of today is find me tabs. There is a tab on Sol where there's a bit of a worksheet on advanced video compression. Last week I mentioned that we were going to do that data moshing thing, if you remember. So that's the first thing we're going to do. So I've put the program there now, and it should boot on these computers because it's a portable sort of standalone-y one. So hopefully you can boot that and have a little look. So fire that up. And if you remember, the idea of data moshing is kind of a stylistic choice and a bit of fun that we do, which is removing the iframes, which often happens by accident in video. So the idea is that we can go through, remove some of the iframes, and you'll end up with the differences to the wrong frame. And that's what we call data moshing. So we can see the effect of that. You will have no doubt seen that before, but it's something to look at. And then after that, we've basically got a little task where we're going to use FFmpeg. I've not given you the commands this time. You'll need to work out how to do them and work out, solve some problems. And we're going to use that to take Big Buck Bunny, which we may have downloaded last week, depending on whether we did or not, or some of the video from last week. It's up to you, any of the examples. We're going to use FFmpeg commands to chop a 20-second section out. Otherwise, if you try and encode the entire of the Big Buck Bunny, you'll be waiting probably around 15 to 20 minutes on these little i3 processors. And then we're going to take that little chunk and encode it to H.265, look at the size difference between those two files, and then see if you can visually see a difference in quality. So you can kind of see what that particular codec is doing. And all of that should be playable with VLC Player.